now that we are oriented with respect to Gaussians, multivariate Gaussians that is, and we know a few facts about them, we got a little intuition for what they kind of look like. So this was, remember, this was way back up here. Here was our definition. And now we're ready to look at the density function for a multivariate Gaussian, well, when in the case that it has a density. But before I get to that, you might be wondering, was it really worth it to define Gaussians in this? I claimed it was a more general way than just to use the density. The density is having a density is kind of a nice thing to work with. Well, it turns out that, in fact, a lot of times the degenerate cases, remember we defined it, a degenerate Gaussian was when the determinant was 0, and that's when it sort of lives in an affine subset, something like this. And these cases do arise in applications, and it's nice to be able to say that those are Gaussians also. And even maybe for another reason is that these degenerate cases arise in the central limit theorem, and rather than having a bunch of special cases, special exceptions and everything, it's nice to be able to remember the central limit theorem that was, Laplace proved in 1810. It's nice to just to simplify the statement of the theorem to say that it converges to a Gaussian. And so oftentimes in mathematics we adjust the definitions appropriately so that the theorems take their the cleanest form if you can adjust the definitions. All right, so let's do the density. All right, so here's the density. We're going to define the density, and then we'll talk about a little bit of intuition for how to remember it and how to sort of think about it mathematically. So a Gaussian random variable x distributed according to, sorry, that was kind of loud. X is distributed normally with mean mu and covariance c, has a density function, if and only if it is non-degenerate, i.e. the determinant of the covariance matrix is non-zero. And in fact, if it's non-zero, it's going to be positive because, remember, C is always a positive semi-definite matrix, or maybe it'd be better to say non-negative definite, but positive semi-definite is sort of the standard terminology, and so the determinant is always greater or equal to 0. And so here's, and in this case, so we'll continue the fact, and in this case, f of x, maybe am I going to have room to put it over here? I'll put it over here. I'll make it nice and big. F of x equals the density is f, 1 over, I'll define this notation in a second, the square root of the determinant of 2 pi times the covariance matrix times e to the minus 1 over 2 times x minus mu transpose c inverse x minus mu. That is the density function for a multivariate Gaussian. And let me define, I didn't really, so it's sort of standard, but just to be clear here, this notation, or in general, this sort of absolute value looking notation for a matrix A is, we write that for the determinant of A. So this here, this part, equals the determinant of 2 pi times the covariance matrix, and when you pull a constant out of a determinant, then the determinant that multiplies the determinant by the dimension, if this is an n by n, so here I'm assuming this is an n by n matrix, mu is in Rn, then it gets multiplied, it's to the power n times the determinant of C. And so sometimes people also write this, they write this denominator here as, so sometimes you see this written as like 2 pi to the n over 2 in the denominator times the determinant of c, the square root of the determinant of c. But that's the same thing as this. But the reason I like this, writing it this way better, because it's so much easier to remember, and by analogy with the one-dimensional Gaussian, right? Because in a univariate one-dimensional Gaussian, the formula is 1 over square root of 2 pi sigma squared, the variance, and so it's just, you don't have to remember all these funny, like, was there the n? Is the n here? Where's the, remembering to put the n? So I like this form better. So that's one trick to help you remember the density. Oh, and maybe I should say, to be clear here, this is for all x in Rn, and here, mu is in Rn, and c is in n by n covariance matrix. Okay, so another thing which so I want to give you some tell you how I remember this formula. So I remember this formula by using this sort of trick here, and also by analogy using the analogy with the one-dimensional case. So if n equals 1, then C, the covariance matrix, it's the covariance of x with itself, and that's just its variance. So, right, because covariance of x with x when x is one-dimensional, that's just equal to the variance of x. And so if you plug in sigma squared for C here, and here, right, C, so C inverse is just 1 over the variance squared. So this becomes 1 over the variance squared. These are each one-dimensional quantity. X minus mu is just a one-dimensional quantity. So this becomes just the usual exponent for the one-dimensional. Let me write it here just for. So the one-dimensional case was 1 over 2 pi sigma squared e to the minus 1 over 2. I'll put the 1 over sigma squared separately, x minus mu squared. So if you just put the 1 over sigma squared in between these two factors, then you get this. So those are two tricks that I use to remember this. And don't forget the inverse, right? You remember the inverse, and you can always remember that it's C inverse because it's 1 over sigma squared for the univariate case. So don't forget the inverse. Now another thing which is, so let me give you a little bit of, okay, so before I get to that, I put the inverse here. Well, it is the inverse, but in linear algebra, whenever we want to invert a matrix, we have to make sure that it is in fact invertible. Not every matrix is invertible, and in this case, it is invertible by our assumption that the determinant is non-zero. Any matrix with a non-zero determinant is invertible, of course. So C is invertible by our assumption that it's non-degenerate. And of course, you can see that that you have to have it non-degenerate in order for this density even to make sense, because otherwise then C would not be invertible. Okay, and now let me give you a little bit of mathematical intuition for this formula. So here's a little bit of mathematical intuition. This use different color. Use red. This sort of exponent here, this thing in the exponent, is a quadratic form. Quadratic. It's called a quadratic form. So, and a quadratic form is a beautiful object in the linear algebra. Whenever, so in general, so let's say quadratic forms. In general, something like this, x transpose ax, not x transpose ax, this is a quadratic form in X when X is some vector, and if you know your formulas for like circles and ellipses and all those things in 2 dimensions. Well, quadratic forms, at least when C is a positive semi-definite matrix, that's symmetric positive semi-definite matrix, quadratic forms are just a very natural extension of those ellipses in 2 dimensions to ellipsoids in higher dimensions. So the level sets of a quadratic form are these ellipsoids in higher dimensions. So I think I want to tell you more about this and draw some more examples, but just to give you some initial intuition, the level sets of a quadratic form, like, well, in this, so I'm not putting the minus mu here, and when you don't have the minus mu, then it's centered at the origin, but the level sets, or the contour lines, those things on the map, the points of constant elevation or constant density in our case, or in this case, it's just where this, so here, the level sets of this function, if I call this a function of x, let's call this g of x, this is a scalar value. It's a scalar value quantity because ax is a vector, and then we take the dot product of x with ax. So this is a scalar quantity, and the sets, the level sets, like maybe this one here, is where g of x equals some constant c, and this would be another constant, and then this one would be another constant, and so on. So the level sets of a quadratic form are these ellipsoids. So in higher dimensions, maybe I could try to draw sort of, a rugby ball looking type of thing. I can, at least you can visualize it in 3 dimensions. So that's what a quadratic form for, so this is when they look like this when C is positive semi-definite, symmetric positive semi-definite, symmetric positive semi-def. They look like these ellipsoids. And why, okay, yeah, that thing shows up in the exponent, and you might be thinking, well, yeah, this looks very similar to what we saw above in the examples. And there's a very simple reason. And the reason is because whenever this exponent takes, on one of these level sets, any 2 points on this level set have the same value of c, so they have the same value in the exponent, and this is just a constant with respect to x. So that means, right? That means that the density would also be constant along those lines. So the level sets. So this is really the key. This quadratic form here. Mathematically, your intuition mathematically, when you think about the density of a Gaussian, it should be very closely linked in your mind to a quadratic form. So in my mind, when I think about, one of these, this Gaussian density, I think about it, as, this is sort of, heuristically speaking, think about it as like e to a quadratic form, or it's at least proportional to e to a quadratic form. So this is, for your intuition, mathematical intuition, how to think about the density of a Gaussian. All right, so I hope that was useful in explaining this somewhat maybe initially intimidating formula. All right, we'll be back. See you next time.